And so I'm pleased to introduce Ljudmila Kamenova to give this talk. So it's the finiteness results for hyperkaehler manifolds.
Thank you very much for the invitation. It's always nice to be here in Montreal. So first, let me introduce our hyperkaehler manifold. Hyperkaehler manifold or also it is called irreducible holomorphic symplectic. This is a compact Kähler manifold M. Which is simply connected. So pi one of them is trivial. And if you take the second homology H20 M, is generated by everywhere non-degenerate holomorphic zero form sigma. Sigma is non-degenerate. Holomorphic two form. And this is why it's also called the holomorphic symplectic manifold, because this is the holomorphic symplectic form that you consider. So when Mark was talking about symplectic geometry earlier, you consider the symplectic form to be the Kähler form, which is 1-1 form. But in our case, for hyperkaehler manifolds, the important form is this 2-0 form sigma, and there is only one such sigma after constant. So notice that because sigma is non-degenerate, then some power of it gives you a trivialization of the canonical bundle. So the canonical bundle is trivial, and this means that the Hertzian class of M is 0. So hyperkaehler manifolds are important class of manifolds with Hertzian class 0. We have the classical theorem which says that it's by Deram, Berger, Bolomov, which says that if you have compact manifold with Hertzian class 0, then some finite cover of it splits as product of tori, calabi-Yals, and hyperkaehlers. So we already learned a little bit about calabi-Yals. Well, for hyperkaehlers, the important property is that we have this holomorphic form, and a lot of the geometry of hyperkaehler is determined of how this H2 sits inside of H2. So a lot of the geometry of a hyperkaehler manifold is governed by second cohomology.
Ljudmila, could you tell us why you call it hyper? Going from this definition.
That's a very good question. There is an equivalent definition coming from differential geometry.
Calabi was 50s.
Yeah,
the one to call.
So I just want to make sure
you ask
everybody understands.
So because the hyper is because there are many complex structures. So the holonomic group is SPN. This is the compact symplectic group SPN. And the quaternions, the group of quaternions acts here. And then from the Coulombic principle, you get a whole sphere of complex structures. So if you have a basis of the quaternions I, J, and K, so with each one of these square is -1, then any complex structure can be represented as some inner combination of this. And because there are so many different complex structures, it's called hyperkaehler because it's Keller to the hyper. So anyway, that's a different interpretation. That's more potential geometric, and that's more algebraic geometric. So, and these two definitions are equivalent, basically because of Yau's solution of Calabi's problem. And even though we have a definition for hyperkaehler, for a while people didn't believe that hyperkaehler manifolds exist other than K3 surfaces. So here's some example. So in complex dimension 2, hyperkaehler manifolds are just K3 surfaces. And Fedya Bogomolov has this famous paper in which he establishes properties of hyperkaehler manifolds. And he says, well, from all these properties, it means that the only hyperkaehlers are K3 surfaces because the properties are too good to be true, basically. But his paper was in the 70s, I think 1978. But then a couple of years later, there were indeed higher dimensional examples of hyperkaehler manifolds. So here's the second example. And right now, these are the standard series of examples that are known. So standard series of examples. They're mostly due to Bouville, although Fuciki independently did one of the examples in complex dimension 2. Sorry, in complex dimension 4. So he has first Huybrechts schemes endpoints on a K3 surface. So if you're not familiar with Huybrechts schemes, that's how you can think of them. These are a minimal singularization of the symmetric product of endpoints, the symmetric end product, and some fixed K3 surface. Modulo the action of the symmetric group of n letters. So basically, here you have endpoints on a K3 surface, and whenever two of them coincide, you get a singularity, and sometimes 3 or more points can coincide at the same time, then you get worse singularity. And then when you resolve these singularities in a minimal way, you get the Hilbert scheme. So that's called the Hilbert-Chow morphism. And that's one series of examples. Then another series of examples is you do something similar for abelian surface. But instead of if you translate Hilbert of an abelian surface, you get something with which is not simply connected, and it will create too many homomorphic forms. So that's what you do. So Hilbert n+1 of some abelian surface. Then you have the Hilbert-Chow morphism, the symmetric n+1 product of this abelian surface modulo the symmetric group as n+1. So this will be the wrong object just because we have too many forms and it's not simply connected. But to make it simply connected, what you do is take the summation map where you sum up these points on the abelian surface because you can now treat it as a group, and so you get a map to A. And then you take any distinguished point or any point, let's call it 0. And then you take the fiber of this composition map, and this is called the generalized Kummer variety, Kn of E. So Huybrechts of K3 has complex dimension 2n. And because Huybrechts n+1 has complex dimension 2n plus 2, then you take the fiber over complex surface, then this one has complex dimension 2n as well. And when you compute the Betti numbers, they have different Betti numbers. So they give different examples. It's not the same example. So basically, in every possible dimension 2n, we get at least 2 different examples. So these examples were established maybe in 81, 82. Then it took a while for people to find new examples. I think O'Grady did them in 99 and 2000, 2001. But here you have the exceptional examples of O'Grady. They live in complex dimension 6 and complex dimension 10. They're more difficult to describe. Basically, you have some moduli spaces of semi-stable objects which are not stable. And they have singularities. So once you resolve the singularities, you get these exceptional examples. You get them as semi-stable sheaves either on a K3 surface or an abelian surface. And then once you resolve the singularities, you get these exceptional examples. So then up to deformation, in every dimension, you have 2 or 3 known examples. And that's all we know in terms of examples of compact Kähler manifolds. So then a natural question to ask is if there are only finitely many examples in each dimension. And considering we don't know very many examples to begin with, the expected answer is yes, that there should be only finitely many examples in each dimension. But what I can prove is that if you fix some invariants, which are topological invariants in each dimension, then they're finitely many. So that's what we'll do. But first, I'll remind you some classical results from topology and from other people in hyperkaehler geometry, what was known before now. Any questions?
You can switch the blackboard situation.
Yes. there is a classical theorem of Dennis Sullivan. This was in the 70s, so 1977. For the homomorphism type, I was simply connected Keller manifold of complex dimension greater than 2 is finitely determined by its integral cohomology ring. So I'm going to say what coefficient is it, and the contracting classes. Okay, so that's the classical theorem in topology. Then, well, maybe 20-something years later, Daniel Huybrechts noticed that for hyperkaehler manifolds, all less information needs to be fixed. So for hyperkaehler manifolds, instead of fixing the whole cohomology ring, you can just fix the H2, and then instead of fixing all the contracting classes, you can just fix the first contracting class. So the first, let me just say that if you take the first contracting class in N, so it belongs in H4 integral class. Then it defines the following homogeneous polynomial. So this defines degree 2n minus 2.
Sorry, what do you mean by finitely determined?
Say that again?
Sorry, what do you mean by finitely determined?
Determined out to finitely many diffeomorphism choices.
Okay, thank you. And just when you want in your question, you wanted to establish that only finitely many up to what? Up to diffeomorphism or up to?
I want to do it up to deformation, but it's for hyperkaehlers, it's equivalent to say that it's up to diffeomorphism.
Thank you.
So in the Sullivan's theorem, you only have finitely many diffeomorphism types after fixing this data. So let's see here for hyperkaehlers. Yeah, if you fix the first contracting class, it defines homogeneous polynomial of degree 2n minus 2 on the second cohomology. By taking a class alpha to well, the intersection or the integral over n of alpha to the 2n minus 2 times the first contracting class. Okay, so because for the hyperkaehler we'll just be fixing the second cohomology, and if we just take the first contracting class, this will be in H4, but since we just fixed H2, what we'll do is fix this polynomial instead. So let's go with polynomial P1 tilde. So here is the theorem by Daniel Huybrechts. From 2001. So if the second integral to homology is fixed as an abelian group, so if this is an abelian group, together with this homogeneous polynomial of degree n minus 2, so P1 tilde, if these two objects are given, then there exists at most finitely many diffeomorphism types of hyperkaehler manifolds of dimension of a given dimension 4n, realizing this structure. Or like this. So there exist at most finitely many diffeomorphism types of hyperkaehler manifolds of dimension 4n, real dimension 4n, realizing this structure. And in the same paper, he proved a couple of different finiteness theorems. So, for example, there exists the following integral, primitive integral quadratic form of H2 MC is denoted by Q. So this one is the Bouville-Bogomolov Fujiki form. Which generalizes the intersection pairing on a K3 surface. So on a K3 surface, if you have two classes in H2, when you intersect them, you get a number. But here in higher dimensional hyperkaehler geometry, when you intersect them, well, you get a class in H4, which well, you can compute it in terms of a number. But if you keep intersecting in various ways with your holomorphic 2 form and it's the complex conjugate, when you do it in some special way, you get the Bouville-Bogomolov Fujiki form. So once you define this form properly, it gives you a generalization of the intersection form on K3 surfaces. And it is phi 3, B2 minus 3. For K3 surfaces, it is of type 319. So here it's also indefinite, and it also has 3 positive vectors, and then the rest are negative. And also it has the following property, that if you have some alpha in the second homology, let me see. Then the top intersection of alpha is some constant. This is a positive constant called the Fujiki constant. Times Q of alpha to the n. Well, for K3 surfaces, that's of course 1, because, well, that's just the intersection pairing. There is nothing to it. But in higher dimensions, it's computed for all of the known examples, and it's always a rational number. Rational number depending on the dimension. So in general, it's a positive real number, but in the cases we can compute it, it's a negative rational number. Okay, so basically, Huybrechts also proved that instead of fixing the first Pontryagin number here, you can just fix this integral quadratic form Q, and then you get finiteness. If you fix the second homology as a lattice together with this quadratic form, then you get finitely many diffeomorphism types. And moreover,
This quadratic form, you consider it to conjugate.
let's see. What do you mean up to conjugacy?
What was that? I don't know. Can you repeat some example?
The whole intersection form. So it's primitive, so you cannot take multiples of it. You want it to be integral, but to be primitive.
Right.
So you fix this as a lattice. So this is some lattice with a quadratic form. But you mean if you take an automorphism of the lattice? Yes, up to automorphism. Yes. So, and moreover, another theorem of Huybrechts. From the same paper is that so we both asked the question here from Zoom that if you fix the diffeomorphism type, there are finitely many deformation equivalent classes for a fixed diffeomorphism type. So that's equivalent for hyperkaehler manifolds. So once the diffeomorphism type is fixed, so let n be a fixed compact manifold. So by fixing the manifold, let's fix the diffeomorphism type. Then there exist at most finitely many deformation types of hyperkaehler structures on M. So for fixed diffeomorphism type, you get finitely many deformation types. But on the other hand, when you talk about deformations of hyperkaehler structures, you either deform the metric or equivalently you deform the complex structure. And for this, we would like to fix the underlying manifold. So we talk about deformations of hyperkaehler structures once you fix the diffeomorphism type. Let me mention what this theorem is based on. So the proof of Huybrechts theorem mostly is the finiteness result of Kohler and Matsusaka. From 1983. So this is the classical result in complex algebraic geometry. So the number of deformation types of projective manifolds M of dimension D. So this is the complex dimension that admit an ample line bundle L with fixed intersections L to the so the top self-intersection L to the D, and then you intersect it with the canonical bundle of M, so then you intersect L to the D minus 1 with the canonical bundle. So you have these two integer numbers. So the number of deformation types of projective manifolds that admit an ample line bundle L with fixed intersections is finite.
So what is deformation here? Yes,
Complex deformation.
just complex.
How do you go from scalar to projective in this?
Well, for hyperkaehler manifolds, you can always deform any scalar manifold for projective one. Because it's a deformation class, the projective ones are dense even. So you can always just deform it to a projective one.
But it is known that it's always projective.
Not all hyperkaehlers are projective, but if you take one which is scalar but non-projective, you can deform it to one that's projective.
How do you see that?
It's another theorem. It's not trivial.
It's not obvious. That's what's.
No, it's not obvious.
So the theorem of Kohler-Matsusaka states it for projected deformations.
You start with a projective manifold, but you can take any complex deformation, right?
But then you get out of the projective world.
Yeah, you get out of the projective world.
Well, their deformation is embedded deformation by the ample line bundle, so it's really a projected deformation.
So Ljudmila, if I have a hyperkaehler and I consider only the complex structures in the hyperkaehler family,
Yes.
you have an argument that projective ones exist and they are dense or something like that?
Yes, there is a theorem that projective ones exist and they're dense. It's also based on a result by Huybrechts, because he basically characterized when a hyperkaehler is projective, and this is if and only if there exists a line bundle with positive Ljudmila self-intersection. So if you take a line bundle L with Q of L positive, this L is not necessarily ample, but there exists another L prime that is ample. So the manifold is projective, but is not necessarily polarization. So that's the characteristic. That's one of Huybrechts' main theorems from his thesis.
For example, on a K3 surface, you could have -2 for this L vanish on some -2, but you could find other.
Exactly. So if you take some L with positive self-intersection on a K3 surface, that's like negative on some rational curve, then this is not necessarily ample, of course, but you choose another L prime, that will be ample. But the K3 surface will still be projected. And it's the same thing for hyperkaehler manifolds. As long as you have some L for which it is positive, then there exists some polarization. L prime, maybe different than so then your hyperkaehler is projected.
Do you have to deform the complex structure in an S2 family, or just you can
Let me think. Yes, you do have to deform it.
no? You have to. I mean, speaking like the K3 picture, actually, if it's a hyperkaehler, you have S2 family complex structure, then each one has this H11 space, right? But if you take the union of this H11, actually the union is the whole H2, so it particularly contains like integral points with right. So even the miss for one is luck, generically miss integral lattice, but
Yes.
if you range over OS2, then you all the integral points are covered.
Exactly. Then all the integral points will be covered. So there will be some deformation that's projected, right? But like the general deformation of a hyperkaehler will be Kähler but non-projective. Then if you take the projective ones, the general deformation will have pK rank 1, then from the projective ones. Then it's stratified, so then pK rank 2 and so on. But this is, and then you can also use Torelli, because by Torelli, you know that everything is covered in H2. Okay. So then Kolar-Matsusaka's theorem becomes a little bit simpler for Calabi-Yau manifolds and hyperkaehlers, because instead of fixing the intersection of L to the D-1 with the canonical bundle, since that's trivial, you don't have to fix this. You only have to fix L to the D. For corollary, if M is a Calabi-Yau or hyperkaehler, then you only need to fix the whole intersection, the whole self-intersection L to the D to obtain finiteness. Okay.
So this Kolar-Matsusaka is like to fix the Riemann-Roch formula.
Yes, exactly. That's how Kolar-Matsusaka proved their theorem. Basically, well, it's a little bit like Riemann-Roch, but really you fix the Hilbert polynomial, and then you see the first couple of coefficients. There's some expressions getting to do with these two numbers. And then Well, then you have to do a lot of work, but that's how you start. Okay. So let me just see how much time I have. Well, let me say a couple of things. Well, for hyperkaehler manifolds, you have to really type theorem. Notice that for K3 surfaces, that really theorem takes the period map from the moduli space of K3 surfaces, but to construct this moduli space in terms of Hoche theory. Here, but for K3 surfaces, fixing the Hoche decomposition of H2 is the same as fixing the complex structure. These two are equivalent. But in higher dimensional hyperkaehler geometry, these are no longer equivalent. So the right type of Torelli theorem for hyperkaehlers is to consider the moduli space of complex structures. So that's the Hybreds space. And if you just take the Hybreds space, it is highly non-Hausdorff. So you have lots of points that are non-separated. So, but by Huybrechts result, two non-separated points in the moduli space correspond to birational hyperkaehlers. For non-separated, it's equivalent to being birational. In the sense that Mark defined for Calabi-Yau. So to make this space Hausdorff, you portion by the equivalence relation being non-separated. And this time it is an equivalence relation because it corresponds to a birational equivalences. So this is called 5-Miller 5B. When you identify, you basically collapse on all the non-separated points, and this is an equivalence relation because they're birational. You take connected component of this, and this is isomorphic to the period domain, which is often non-singular quadric inside of the projectivization of H2 M complexified, so C, like this. Anyway, there is the better description of the period domain, either in terms of a quadric, or you can also write it as a quotient of two Lie groups, non-compact Lie groups. So anyway, the good thing is we have a Torelli theorem for hyperkaehlers. So basically, it's surjective, and it's not only a local isomorphism, it's a global isomorphism. It is set up directly like this. Okay. Now, let me also say a few words about fibrations. So, by Matsushita's theorem, you have the following. Let's take M to be a hyperkaehler manifold, and you have a vibration towards base. So let's assume that this is the vibration. What is a fibration? Fibration is the proper surjective morphism with connected fibers. And you just assume that the dimension of B is strictly between 0 and the dimension of M. Then Matsushita proved that the dimension of B is precisely 1/2 the dimension of M. The general fiber is an abelian variety.
So what are M and B here? Is what is our
M is hyperkaehler,
okay?
and B is any complex variety, could be singular. But the important thing is that you have a fibration structure. So the general fiber is an abelian variety. Even if M is hyperkaehler, which is non-projective, just scalar but non-projective, the fibers are still projective. They're projective tori. So it's an abelian variety, which is Lagrangian. With respect to sigma, which was the H, the 2-0 form. Then Huang proved that if you assume that this complex space B is smooth, then not only is half of the dimension, but it's complex projective space. So if M is hyperkaehler of complex dimension 2n, this B of complex dimension n is the same as complex projective space, assuming that's smooth.
With your examples fit into this.
Yes, all the examples we have, for all the examples B is smooth, and we don't have an example for which B is singular. So we conjecture that B is always smooth.
So this is up to the formation of the complex, initial complex structure through this family, I guess. You always have such a.
Yes. And so far, when N is 2, then it's a theorem that B is always smooth. That's the work of many people, like O, Huybrechts, Chen Sha. So they use the minimum model program and classification of fibers to show that if N is 2, then indeed this is always smooth. But in general, we don't have hope of solving this anytime soon. But that's the conjecture, that it's smooth.
Some known results when this vibration has a section.
Yes, so that's correct. Sometimes it has section, but sometimes it doesn't. It's a cohomological construction.
You don't expect that this section is Lagrangian also?
Yes, exactly. If it exists, it's Lagrangian. It's a very good observation. So let me just state a bunch of theorems that we have. One of them is joint with Ljudmila Kamenova. So take M to be a fixed compact manifold. So we fix the diffeomorphism structure. Then there exists only finitely many, or at most finitely. So there exists only finitely many deformation types of hyperkaehler Lagrangian fibrations. And we consider the empty space finite as well. So there could be none. So this is the analog of Huybrechts theorem, in which he says that if you fix the diffeomorphism type of a compact manifold, then there exists only finitely many deformation types of hyperkaehler structure. And then we generalize the Huybrechts theorem, some of his other theorems about finiteness, by instead of fixing the whole lattice H2, I just fix two things about the lattice. So that was in 2015. So there are at most finitely many. Deformation classes of hyperkaehler manifolds M, let's say a complex dimension 2n with a fixed Fujiki constant Remember, this was this positive number that only depends on the topological type of the manifold, appearing in the Fujiki formula. And the other number in fixed is the discriminant of the Bouvier-Bogomolov-Fujiki lattice. So n given discriminant of the Bouvier-Bogomolov-Fujiki lattice. Let's call it lambda. This is just each two of your hyperkaehler manifold together with Q. So instead of fixing the whole lattice and the whole form, just fix its determinant. So you fix two numbers, I mean, other than the dimension. So you fix the dimension, and then you fix the Fujiki constant, which is topological invariant, and then the discriminant, which is also topological invariant. And then you get finiteness. So that's one theorem. Let me see if I have more time. Oh, I have time to formulate two more theorems. So basically, Huybrechts theorem was based on Kolar Matsusaka. And I base my theorem on a refinement of Kolar Matsusaka which was given by Francois Charles. And then another theorem. Also from the same year, is that, well, if you want to consider fibrations, then you can just fix one invariant instead of two. So, consider Lagrangian fibration. And let's assume the base is smooth for simplicity. So from M to CPM, such that there is a line bundle P on M with Q of P positive and given P degree on the general fiber of pi. So given P degree, which is P to the N times F, where F is the general fiber, let's fix this number to be D. So then there are most finitely many deformation classes of hyperkaehler manifolds with this data. So then there are only most finitely many. Deformation classes of hyperkaehler manifolds. M as above. So this a theorem about specifically Lagrangian fibrations. And I have more minutes, so I can give you one more theorem, again specifically about Lagrangian fibration. This is from this year. Actually, I did it last year, but forgot to put it on the archive until this year. So, last theorem, consider a Lagrangian fibration pi from M, and again, for simplicity, let's assume the base is smooth for CPN with a discriminant divisor D. D in CPN being the discriminant divisor. And let's assume that it has at worst simple normal crossings of singularities. Then there are at most finitely many Lagrangian fibrations with this given discriminant divisor. So let's call this other vibration phi prime and N prime CPN with this given divisor. So that's another way to think about finiteness. Well, what if you is the singular set, the set of the base that has singular fibers above the set? Well, once you fix it, you also have finiteness.
What is the dimension of the fiber?
It's also n. So
Okay.
the base is half dimension and the fibers are half dimension.
Could you? I'm sorry. How do you define the divisor then?
Inside of CPN, this is a locus of codimension 1 where all the singular fibers live. One can prove that the set of singular fibers is either empty or codimension 1, and it cannot be empty because then you don't have simply connectedness.
Okay, it's okay. It's the singular divisor.
Yeah. So these are the finiteness theorems we have so far in the past and present. It would be nice to put them without any assumptions. But so far, that's what we have.
So, are there other questions or remarks? Yes, let's see.
I have a naive question. So you mentioned these exceptional examples of O'Grady coming from moduli spaces, semi-stable sheaves.
Yes.
What about the standard examples? Are they also can be seen as
Yes, they're
moduli space?
also seen as moduli spaces, but of stable sheaves.
Okay. And what about if we allow the stability notions to consider like Bridgeland stability and so on? Can we imagine to get more examples out of this?
One can try this approach, yes, but then the singularities might get too bad to be resolved simply.
Yeah. So the tricky argument is then to resolve the singularities and to show still that you have holomorphic symplectic form on the resolution. Is that?
Yes, that's right. So, and a couple of people, Manfred Len and Dima Kalendin, they proved that if you take moduli spaces of semi-stable sheaves with different parameters like different C1 and different C2, if you resolve them, you can never get new examples. The only new examples you can get are these specific two examples that O'Grady produced. But if you get different first rank class and second rank class, basically you vary the Mukai vector. So if you take a different Mukai vector, you cannot produce new examples.
So is there a conceptual explanation of this miracle? Or
it's very technical. So it's a technical paper.
Was on through some relations between these examples. I don't remember what she proved. That she proved, I think a few years ago, she proved that, like, I don't know, birational relation between the three families, some number three family deformation equivalent or birational equivalent or something. I forgot.
I don't think they're birational equivalent because they have different cohomology and different Betti numbers. But maybe she gave different birational models. So yeah, I'm not sure. But yeah, their Betti numbers are different, so they're not birational.
Other questions? Yes.
I want to ask you about fibration theorem. So in the case of dimension 2, there is like a K2 surface to CP1.
Yes.
So this fibration is always isotrivial.
Oh no, it's not always isotrivial. That's actually a good theorem. Let me give you one more theorem.
Plus K else is 0. The unit of the push port is 0. So there are no upper parts.
So for a while, this was a conjecture by Matsushita. But now it's the theorem of Ben Bakker. That any Lagrangian vibration on a hyperkaehler manifold is either isotrivial or of maximal variation. And the general Lagrangian vibration is a maximal variation. Isotrivial ones are very special. So there is nothing in between.
Do you have an idea? Can you give an idea of what is isotrivial?
Isotrivial means that
Some other
all of the fibers are the same abelian variety.
Okay, but in the case in dimension 2, cannot have maximal variation.
Oh yes, you can. You don't have to have the same elliptic curve.
Are you sure?
Yes.
She seems to be sure.
That's the general case. The general case for K3s and hyperkaehlers is maximal variation. So here, if you take a hyperkaehler manifold M or a K3 surface, vibration CPN, there is rational map to the abelian to the moduli space of abelian varieties N with a given polarization alpha. And so if this maps here to a point, then you have isotrivial. But if this maps to higher dimensional locus, then the dimension of this locus, the only possibility is that the dimension of the image is also n, and that's the maximal variation. And the general case is of maximal variation. Before Ben Bakker, Claire Vozan and Van Hieman made some progress. They proved that a general Lagrangian vibration on a hyperkaehler manifold is either isotrivial or maximal variation, and more precisely, like the most general version of a Lagrangian vibration always has maximal variation because it has to do with something called the Manford-Tate group, and the Manford-Tate group is maximal for a general hyperkaehler vibration. So then you get the maximal case here.
So another general question. So you have some information about the recent advance in birational geometry of hyperkaehler manifold, projective manifold. Do you have some ideas? What is the progress recently?
Good question. I know the classical result that birational hyperkaehlers correspond to non-separated points. More precisely, in complex dimension 4, they're related by Mukai flows. So similar to the flows you were discussing, in hyperkaehler geometry, we have Mukai flows. So in complex dimension 4, you can just do a series of flows. But in higher dimensions, we don't know. But it's possible you'll do a series of Mukai flows. That for sure will produce something birational. But whether all birational ones are related by flows, we don't know.
Thank you so much.
Yes, Zakaria.
I want to come back to Sullivan theorem that we said at the beginning. You said that the diffeomorphism type of simply connected Kähler manifold is finitely determined by its cohomology groups and contour eigenclasses, right?
Yeah, but simply connect.
Yeah, simply connected. So I was wondering, how can topological data determine completely the diffeomorphism type of a manifold?
Well, it's true for surfaces.
It's-
Yeah, for real
Yeah.
surfaces. That's what it happens.
And the second question is, it's finitely determined. I don't know what's happening in other dimension, but for example, for example R4, it admits infinitely non-countably differentiable structure.
Yes, that's like you assume that the complex dimension is bigger than 2, so real dimension is bigger than 4.
So in other dimensions, we don't know what's happened.
Yes, I read his paper once. It's in the publications of IHES. He has some clever ideas, but it's difficult for me to reproduce them.
Let's use the H-cobordism theorem somewhere. That's the sort of engine that drives a lot of this sort of stuff.
Yeah, but it seems to me that it's weird that only the cohomology and contour eigenclasses determine.
No, but it's in a very specific context. Hyperkaehler manifolds with class. Yeah. You start from this.
Sullivan's theorem.
She said.
Oh, the Sullivan theorem. Sorry. Oh, yeah, you're right. Sorry.
Yeah, it is very strong theorem, right?
And it's surprising. It's surprising.
Yeah, oh, he has some good ideas. I mean, great ideas.
In the higher dimension, there's only a finite number of smooth structure on a given topological manifold. It's just
Sorry?
in dimension 5 or 6 and higher, the number of smooth structures is just finite on a topological manifold. It's a general theory in the 60s and 70s.
It's a kind of a H principle, is it?
H cobordism, I think.
Oh, H, yes. Well, there's an H somewhere. Yeah.
Yeah, H somewhere. So this is just dimension 4 is very exceptional. But in other than dimension 4, you always have finiteness structures. Okay, so at least first of all, so you just need to determine the topological manifold, the topological type.
So, in other words, the topological category and differentiable category.
Yeah. There's a finiteness difference.
Other questions? Okay, so let's thank Ljudmila once again.